Okay, so we're going to start chapter 3 here with a little bit of a review from chapter 4 since we did that first. Okay, just a quick reminder of what a response variable is versus an explanatory variable. Remember, our response variable is what we call our dependent variable in science. Okay, so our response variable is measuring the outcome of what's going to happen from the experiment, where the explanatory variable is our independent variable in science, and it's the one that may cause the change. Okay, and so let's look at a quick example here, linking SAT math and critical reading scores. Julie asked, can I predict a state's mean SAT math score if I know the state's mean SAT critical reading score? Jim wants to know how the mean SAT math and critical reading scores this year in the 50 states are related to each other. Identify the explanatory and the response variable here if possible. So again, our explanatory variable is the one that causes the change, where the response variable is the one that is affected by it. So with Julie, these are two separate scenarios here. So with Julie, she wants to know if she knows this reading score here, can she predict the math score then? So for Julie, the explanatory variable here is the critical reading score. And her response variable is going to be the SAT math score. So her response variable is that math score. Whereas for Jim just wants to look at the relationship between the two. So he has not set aside like this one particular one affects the other. So for Jim, there is no clear explanatory or response variable. He is just looking to see if there is a relationship. So let's look at these two quick examples here. So the first one, how does drinking beer affect the level of alcohol in people's blood? Okay, so in this particular experiment here, your explanatory variable would be the amount of alcohol, and your response variable would be blood alcohol levels. How do those change based on the amount of alcohol that was consumed? So the second one, the National Student Loan Survey, provides data on the amount of debt for recent college graduates, their current income, and how stressed they feel about college debt. Okay, so the sociologist is looking at the data with the goal of using the amount of debt to explain the stress caused by college debt. So in this particular case, my explanatory value then would be my amount of debt, and my response variable then would be the stress that is caused by that college debt. Okay, so let's take a look at a scatter plot now. We've practiced drawing a variety of graphs at this point. We've practiced drawing dot plots, histograms, box plots, and stem plots. The difference between those and a scatter plot is that those are all for one quantitative variable, one variable that you measured, where your scatter plot is going to be for two quantitative variables. So that's kind of a key point to remember. This is the only kind of graph you can draw when you are drawing a graph to show the relationship here between two quantitative variables. And what that means is two variables that you were able to measure. Okay, two variables that you have measurable values for. And they're done on the same individuals. Okay, and so when you're drawing these, this is what your typical graph is that you've drawn in science class. Okay, you've got your explanatory variable down on the x-axis, your response variable over on the y-axis. Okay, you'll notice that each axis is clearly labeled. Okay, scale is consistent throughout. The one on the bottom goes by tens the entire way. The one on the top is going by, the y-axis is going by 25s. You'll notice the axis doesn't always have to start at 0. A lot of the times one of them will not start at 0. Sometimes both of them will not start at 0. As long as that scale stays consistent and you're not going like this range here is 10 and then I'm at 50 and then I'm at 5 and then 60. As long as that scale of our axes stays consistent, then you are fine if it doesn't start at 0. Okay. Remember to clearly label them. These are another type of graph that you'll be able to create on your calculator, but if you don't label the x and y axis, again with units like always, then you wouldn't end up getting full credit. You would also need your good scale there as well. What you'll also notice is that we did not draw a line connecting all of these dots. Okay? There is no line of best fit. There is no line, connecting every data point on here. Okay? You are just plotting the data points, and then we'll look at analyzing those and seeing if there's a relationship between them. Okay, so let's look at this example of making a scatter plot. So at the end of the 2011 college football season, the University of Alabama defeated Louisiana State University for the national championship. Interestingly, both of these teams were from the Southeastern Conference. Here are the average number of points scored per game and number of wins for each of the 12 teams in the SEC that season. So we've got two quantitative variables here, two measurable variables. We have points per game, and then we have wins. Okay, so both of those are forms of measurement. So the first thing we need to do to be able to do a scatter plot of this is we need to decide which of these goes on which axis, which is our explanatory value variable and which one is our response variable. So in this particular case, our points would be our explanatory value variable, and our wins would be the response variable. We're trying to see if there's a relationship between the amount of points they scored and the amount of wins that they had. Our next step after that would be to scale and label the axes. So the first thing we're going to do, is we're going to which variable on which axis. And then we're going to scale and label our axes. Remember, they don't have to start at 0. They just need to be consistent. And then from there, we're going to plot every single individual data point. And so you should end up with a graph that looks, if I can grab it, that looks something like this. We've got points per game down on the x-axis. On the y-axis, we have our wins. Wins might have started at 0, but you'll see the scale is consistent going by 2s. Points per game, our scale is consistent starting by 5s, but it did not start at 0. And then we plot all of our individual data points. Like you can see, for instance, here, these lines here indicate where the data point for Alabama is. Alabama was about 34.8 points per game, and they had 12 wins. Okay, so now that we can draw one, we have to be able to describe one just like before. So remember, with our single variable quantitative data, our histograms, our box plots, stem plots, we were cussing those graphs. We were giving our center, we were looking for unusual features, we were looking for shape, we were looking for spread. Okay, when we're examining a scatter plot, we're going to sit on the sofa. So when we examine a scatter plot, we're looking for strength. Okay, and so by strength, we're looking at basically how close do they follow the form. And we'll look at what that means in a little bit. But we're looking at how closely they follow whatever form has been determined. Okay, so if we look at this particular data set that we have here, let's see if we make this a little bigger. So looking at what we have here, these have a slightly curved form. And they do a pretty good job of following it. They're not super tight together. Okay, so we'd say this graph had a moderate strength. Okay, but that's what we're looking for. We're looking for strength, is how close they are to the form. Okay, so the form, you can think of form similar to shape. Okay, so the form is our F here. So the form in this case is slightly curved. Okay, and then our O is outliers. So looking for things that fall way outside the unusual pattern. So these would be Maine right here. So Maine down here in the corner, as well as West Virginia right here. Okay, falling a little bit outside the pattern. The pattern would really kind of go like this. Okay, and so the last thing is our A, which is our association or direction. So for this, association or direction. So in this case, we would say we have a negative association. It's moving from the upper left down to the lower right. So they have a negative association. Okay, as the score is going down, okay, as the mean math score is going down, the percent of kids taking the test goes up, it's higher. Or really it would be the other way around. As the percent taking the test goes up, because this is my explanatory variable, the mean math score is going down. So our association in this graph is a negative association between the two variables. So strength is how close it follows the form. Form is the basic shape or pattern. Outliers, and then our association. So let's look at another example. Okay, so let's look at an example of this. This goes back to the SEC question before. Okay, so with our SEC points per game versus the win relationship here. So this time we're asked to describe it. So if we're using our acronym here, if we're using our SOFA, we're going to start with the S. Okay, we've got our SOFA. We've got strength, outliers, form, and association. Really, we can start anywhere. Okay, so if we look at this, it seems basically our form is basically linear. I would say that the strength of this is fairly strong. There don't really appear to be any outliers. It stays in a pretty good linear pattern. There doesn't really seem to be any outliers. So there would be no apparent outliers. And this time, our association would be a positive association. Our direction here is that the more points per game, the more wins. So it would be a positive association. And what would be key here is that we would need to make sure that we were using our context. Have to use the context. So when we talk about our positive association, we would need to say, there is a positive association. The more points per game, the more wins. They have basically there is a linear shape that is fairly strong, and there does not appear to be any outliers. Context is a must, though. You have to make sure that you use it to get your full credit. Okay, so I think you already have these figured out. To me, they're pretty intuitive, but let's just make sure. So we're talking about positive association versus negative association. So with a positive association, if we've got our graph here. So with a positive association, above average values, so high values for one, usually accompany high values for the other. So high values go together. And then below average values for both of them also tend to go together. So you'll end up with that look like that for your positive association. Where a negative association, I'm going to have above average values of one, but below average values of the other. So for instance, if I had high on my x-axis, I would have low on my y. And if I had high on my y-axis, I would have low on my x. So my negative association ends up looking like that. Okay, so this example asks you to do all things together. I'm not going to draw a scatter plot for you on the iPad here. It will end up looking like a big mess, so I'm going to use the picture. But the problem here asked us to make a scatter plot and then show the relationship between the number of manatees killed and the number of registered boats, and then describe what we see. That's a key thing to realize. I've got 3 sets of numbers here. I've got year, boat, and manatees. But I need to realize that I only need to use the number of boats, and then the number of manatees that were killed, because that's the relationship that it's asking me for, is the relationship between the number of manatees killed and the number of registered boats. So my explanatory value here, variable here, would be the number of boats, seeing if that makes an impact on my response variable, which is the number of manatees killed. When I go through and I plot all this data, this is what I end up with, over here. So I end up with all these various data plots, and then you're asked to describe it. So if we're going to describe it, we're going to use our acronym, and we're going to see what we have going on here. Remember, we're SOFA, and we're going to use our context. Make sure you use your context. So let's look at what we have going on here. There's a positive association. That's an is. And so I would use my context here. That's the best place to use my context. There's a positive association. I'm going to shorthand some stuff here as registered boats increased, increase in manatee death. Remember, you would need to use all of that context. So the number of registered boats in Florida, you're not talking about registered boats in the whole U.S. or in the southeastern U.S., registered boats in Florida, there's an increase in manatee deaths. So there's a positive association. More registered boats, more manatees are killed. My form here is basically linear. So I have a linear form here. And it's relatively strong. The points don't really deviate too far from the line. It's all basically right there in that straight line. We've got a couple of years where we had a lot of boats registered, but not as many manatee deaths, this little hunk right here. But they are still pretty close to our line. I'm not sure I would even consider those outliers. That's going to be a judgment call. You do not have a specific equation to determine outliers like you did before. So that will be a judgment call. So our form here would be linear with a pretty strong linear relationship with doesn't look like any outliers. You may want to mention that you have these four here, but they don't deviate extremely from the line. Okay, so the next concept we're going to look at is correlation. So correlation is represented by a lowercase r. So correlation is a way to measure the direction strength of the linear relationship between the two quantitative variables. So before we were kind of eyeballing it, we would say that it looked like it was pretty strong. Maybe it looked like there was a few outliers. But eyeballing it isn't so great. If you look at this example here, you can see why. These two examples here are the same, just one is the scale is different. If you look at the scale on both x and y axis, you'll see that it's different. So that essentially I get a zoomed in versus a not zoomed in. Where it could look, one could make it look like it has a stronger correlation than the other. So we're going to look at how to measure that. So let's look at what some correlation measurements look like so we can start to kind of see how that will shake out. So you'll notice they can be positive or negative. So they can be, they can be positive or they can be negative. Negative ones show that negative association. Positive correlations show that positive association. Correlations will be between 0 and 1. The only way you will have a correlation of, well, actually they would be between -1 and 1. The only way you would have a correlation of -1 or of 1 is if they were in a perfectly straight line. You can see this one down here in the bottom right. Is a correlation of -0.99. They are almost in a straight line, but they are not quite. There are some that are still a little bit off. To get that true -1 correlation, they'd have to be in an exact straight line. You'll notice the tighter they are to the line, the higher the correlation is. So you can see up here, I've got a correlation of 0. I don't have much of a line at all. I'm starting to get a little bit more of a linear relationship here, so I get a low correlation. They're coming a little bit tighter here, and so I get a kind of a medium correlation there. Again, a little bit tighter, a negative though, so a -0.9 or 0.7, and then again tighter here with a 0.9. That's one of the things you can do, okay, is you can draw a circle around your points, and the more oval your circle is, the stronger the correlation. The more circular, like this, that your circle is, the lower the correlation. Okay, so let's look at this example here involving correlation. So back to the SEC football example, our earlier scatter plot of the average points per game and number of wins for college football teams in the SEC is repeated at the top right, so it's over here on the right for us. For these data, our correlation here is R equals 0.936. That's a pretty high correlation, so that would be a pretty strong linear pattern there. So part A asks us to interpret the value of R in context. So if we're interpreting the value in context, it's a pretty high number. So we would say that it's a strong, positive, linear relationship, and then we put in our context, right? So it's strong because it's a high number with a 0.9. There's not really a firm rule here. We're going to go kind of with like a greater than 0.7. Both positive or negative. Well, that's hard to say greater that way, but a larger digit than a 0.7. Whether it's positive or negative, we'll go with a strong, and then kind of a 0.4, 0.5 to that 0.7 would be a medium, and then it would be a weak correlation below that. It's a positive association, right? It's a positive number. So that tells me it's a positive association. Okay? And then I use my context here for what this is. And it's between my explanatory variable and my response variable. So between points per game and wins in the SEC. So explanatory variable and followed by the response variable. So part B asks tells you that the point highlighted in red is Mississippi, which is this one down here. Okay, what effect does Mississippi have on the correlation, and justify my answer? Well, in this case, what we're looking at here is I'm looking at my line here, okay, and my line would go through here. So I would say that Mississippi actually makes the correlation stronger. Mississippi is very close to the line, if not on the line, okay? And so Mississippi increases the strength of the correlation. If Mississippi was not there, then we'd have one less point that's really close to the line, okay? So these points that are out here, they would lower the correlation. So Mississippi actually strengthens the correlation because it is so tightly clustered to the line. Okay, so let's look at an example here. There's 4 graphs here, but we're only going to look at 2 of them. You're asked for each graph to estimate the correlation and then interpret the value of R in context. So we're going to look at graphs A and graph C here. So graph A is the manatee plot that we did before. So let's look at our correlation here. So I know it's going to be a positive number because I'm going up like this. If I draw an oval around my data, that oval is pretty narrow. So it's going to be a pretty strong correlation. So I would say for A, we've got a correlation that's approximately 0.9. Okay? And then when I interpret it in context, then I'm going to say that what this means is that I have a strong positive relationship between the explanatory variable and the response variable. So I have a strong positive relationship between the number of boats registered in Florida and the number of manatees killed. So let's look at C then. So for C, C is a little bit tougher. My circle here is a lot more of a circle, less than an oval. So my correlation is going to be a lot lower. Okay, we have a correlation here of approximately 0.3. Okay, and so what that means in context is that there is a weak, but it's still positive. So there is a weak, positive, linear relationship. I really should have said linear up here too. Weak, positive, linear relationship again, using my context between the explanatory variable and the response variable. So between the healing rate of limb 1 and the healing rate of limb 2. This was about the healing rate of front limbs in a kind of newt during an experiment. So with a low correlation like that, a close to zero correlation, I have a weak positive linear relationship between the healing rate of limb 1 and limb 2. So now, what if you're asked to to calculate correlation? If you are, you're hopefully going to be using your calculator to do that. Okay, but remember, for showing your work and stuff, you need to know what the formula is and what it looks like. And let's look at what's happening with this formula here. Hopefully the parts of this formula look familiar. This part right here and this part right here. Those are both z-scores. Right? I took my data point and I subtracted it from my mean, divided it by my standard deviation. And then I took my data point, subtracted it by my mean, and found divided it by my standard deviation. Basically, you went through and you standardized the x and the y value for every data set. So, for example, in the SEC football situation, you standardized the x and the points per game and the wins for Alabama. And then you standardized them for Arkansas. And you went all the way through every single team, okay, and you standardized the X and the Y for every single team, multiplied those together, added them, and then you'll notice you divide. It's an average. Correlation is an average, basically, of all the products of the standardized scores for the teams. It's an average of all the products of the X and Y z-scores for all the teams. Okay, so let's get the last few things down here about correlation. So first of all, correlation does not care which one the explanatory value is and which one the response variable is. If you think about the formula, you're multiplying those two things together. So those two, it doesn't matter which one you're calling X and which one you're calling Y. So correlation does not care about which is which, okay, which can be important later. Okay, because when you find the correlation, when you find that value using z-scores. So your R does not change if you change your units of measurement on the X or the Y. Your R won't change because you're using z-scores to do that. So if you change, so R does not change if you change the units of measurements. So if I went from, well, our SEC, nor does our manatee example work very well. Let's say I was testing the correlation between wingspan, so how long your arms are from fingertip to fingertip, and height. And if I first measured it all in inches and then I changed it to centimeters, okay, my R wouldn't change. The correlation would not change. Okay, R is just a number. There are no units associated with R. Okay, no units associated with R. It is just a number. Also remember that it does not imply causation. It does not imply causation. There may be a correlation, but that doesn't mean that one caused the other. I could see a correlation between, let me think of something, as the amount of hours that teenager plays Fortnite increases, then their height increases. That doesn't mean that Fortnite playing causes their height to increase. It just means that Fortnite has become more popular, and so people play it for lots and lots, and most people hit a growth spurt during their teenage years. That does not mean that one, just because there's a correlation, doesn't mean that one causes the other. That's one of the things that I think is key if you kind of look at statistics that are out in the real world. Okay? They might show you a correlation so that people might think there's a causation, but that doesn't mean that there is just because there is a correlation. Okay? Remember, this is only for two quantitative variables, So correlation doesn't work if your variables are not quantitative. So it only applies to two quantitative variables, and they have to have a linear relationship. It doesn't necessarily have to be strong, because that's what correlation does, is measure it, but two quantitative variables with a linear relationship. Okay. Correlation also, let me clear some space out here. Okay, so in addition to these quantitative linear variables, a correlation is also not resistant. So remember, mean and standard deviation were not resistant, just like we saw with the Mississippi thing. Okay, so correlation is not resistant. 1 point can affect it. So large outliers could definitely pull the correlation one direction or the other. Okay, and it is not a complete summary of the data. If you are asked to give a complete summary of the data, you can give correlation, but you also need to make sure that you are giving the mean and the standard deviation, the mean and the standard deviation of both values, the mean and the standard deviation of x, as well as the mean and the standard deviation of y. That would be a complete summary. Mean standard deviation of x, mean standard deviation of y, as well as the correlation. So I think that's enough for today, and we'll stop here, and we'll pick up with 3.2 next time.